Mole calculations involving gas volumes for AQA GCSE Chemistry. We will start with a review of the idea of the reacting mole ratio, look at units of gas volumes, the idea of the molar gas volume, then calculations involving moles and volumes, volumes in reaction equations, and then gas-only equations. The reacting mole ratio is the ratio in moles of each substance reacting and being formed in a chemical reaction. And of course, this is seen in the balanced chemical reaction. For example, the reacting ratio between hydrogen and oxygen is 2 to 1, and the formation of water is 2. So we have a ratio of 2 to 1 to 2. That's the reacting ratio, but it is a reacting ratio in moles. So 2 moles of hydrogen reacts with 1 mole of oxygen to form 2 moles of water. That is a fixed ratio. It is always 2 hydrogens to 1 oxygen to 2 waters. Regardless of the amounts actually involved, the ratio will always be 2 to 1 to 2 in moles. Firstly, we need to discuss units of gas volume. So there are 2 volume units interchangeably used, centimeters cubed and decimeters cubed. 1 decimeter is equivalent to 1,000 centimeters cubed, and 1 centimeter cubed is equivalent to 0.001 decimeters cubed, in other words, 1,000th of a decimeter cubed. It's necessary to convert between centimeters cubed and decimeters cubed. So pause the lesson and complete the conversion table. 200 centimeters cubed, how many dm cubed, how many decimeters cubed? 3 decimeters cubed, how many centimeters cubed, etc. Okay, there are 4 conversions. Pause, come back to check and correct when you are ready. Okay, so I'm going to reveal the first answer. 200 centimeters cubed is 0.2 decimeters cubed. 3 decimeters cubed is 3,000 centimeters cubed. 25 is 0.025 decimeters cubed. And 0.05 decimeters cubed is 50 centimeters cubed. Molar gas volume. The volume of gas, of any gas, is not decided by the molecular size, but by the numbers of particles. Now, at all times at GCSE, we will be working at room temperature and pressure, RTP. So we have constant temperature and pressure. So if we look at my picture, we've got 7 gas particles on the left and 7 gas particles on the right. The gas molecules are of different sizes, but the volume occupied is the same. The same number of gas molecules occupies the same volume. This is because the volume is principally decided by the distance apart of the gas molecules. The size of the gas molecules has no impact on the total volume. By experiment, the volume occupied by 1 mole of any gas has been determined, and 1 mole of any gas occupies 24,000 centimeters cubed. This is called the molar gas volume at room temperature and pressure. So 1 mole of any gas occupies 24,000 centimeters cubed. You'll be using that figure in gas volume calculations. Alternatively, 1 mole of gas molecules occupies 24 decimeters cubed. Again, you will be using that figure in volume calculations. They're the same volume, but different units. So we've been through reacting mole ratio, units, and molar gas volume. We'll now see how to convert between moles and volume and moles. So we are going to use the molar gas volume to calculate the volume of any gas. The molar gas volume is 24 decimeters cubed. I'm going to work in decimeters cubed at the moment. It's simply the number of moles times 24 will give you the volume of any gas in decimeters cubed. So let's do an example. What is the volume of 2 moles of hydrogen gas? Well, 2, that's the numbers of moles, times 24, that's the molar gas volume, comes to 48 decimeters cubed. Convert that into centimeters cubed, 48,000 centimeters cubed. So here's an incomplete table. 5 gases. We've got the numbers of moles for 3 of them and the volume for 2 of them. Could you calculate the volume occupied by the number of moles and the numbers of moles that reflects the volume? Pause. Complete. Come back to check and correct when you are ready. Okay, so the first answer is 6,000. I got that by 0.25 times 24,000. 1.5 moles is 36,000 centimeters cubed. That's 1.5 times 24,000. I hope it's seemingly obvious. 12,000, 0.5 times 24,000. But what about this next feature? How do we calculate the numbers of moles? Well, we're simply going to rearrange this equation so that we isolate the number of gaseous moles as equaling the volume of gas divided by 24,000. All I've done is bring down, divided both sides by 24 decimeters cubed or 24,000 centimeters cubed. So numbers of moles is the volume divided by 24,000 if the volume is in centimeters cubed, and I am working in centimeters cubed. So if you haven't completed these two, pause and complete. If you have, and you're now ready, here's the answer, 0.1. That's simply 2,400 divided by 24,000. And similarly, 1,200 divided by 24,000 is 0.05 moles. So from the volume of a gas, we can calculate the numbers of moles. From the numbers of moles, we can calculate the volume of gas. Simply using this or rearranging this relationship, the volume of any gas is the numbers of moles times the molar gas volume, 24 decimeters cubed, or 24,000 centimeters cubed. The volume of any gas can also be calculated from its mass. For example, calculate the volume of 4.4 grams of carbon dioxide, CO2. Well, the first step is to convert the mass into a number of moles. So that's 4.4, the mass, divided by 44, the molar mass. That comes to 0.1 moles. Then step 2, convert the numbers of moles into a gas volume as on the previous slide. numbers of moles times the molar gas volume in decimeters cubed or centimeters cubed comes to 2.4 decimeters cubed. Just to be absolutely clear, where does the 44 come from? 12 for carbon, 2 times 16 comes to 44. So that is the relative molecular mass of carbon dioxide, which in grams is the molar mass. So the mass of 1 mole is 44 grams. So 4.4 divided by the mass of 1 mole. The molar mass comes to 0.1 moles. So here's a task for you. Calculate the volume of 0.32 grams of sulfur dioxide SO2. Pause. Complete the calculation. Come back to check and correct when you are ready. So I'm about to reveal. Moles of sulfur dioxide, 0.32, that's the mass divided by 64, just to be clear. Sulfur is 32 and 2 times 16 for oxygen. That comes to 64. So 1 mole is 64 grams. Comes to 0.005 moles. Step 2, volume of sulfur dioxide is the numbers of moles times the molar gas volume, 24 decimeters cubed or 24,000 centimeters cubed, but for ease of presentation I've used 24, comes to 0.12 decimeters cubed. So we can convert a mass into a numbers of moles and then convert the numbers of moles into a gas volume by multiplying by the molar gas volume. We can use molar gas volume to calculate reacting volumes of gases from a balanced chemical equation. Let's start with a model problem. Calculate the volume of carbon dioxide produced by the decomposition of 8.4 grams of magnesium carbonate. So we need a balanced chemical equation, and within that we can see that 1 mole of magnesium carbonate produces 1 mole of carbon dioxide. The reacting mole ratio is 1:1. So the first step is to convert the mass of magnesium carbonate into a numbers of moles. So 8.4 divided by the molar mass of magnesium carbonate, 84, comes to 0.1 moles. Predict the moles of carbon dioxide produced using the reacting mole ratio. Well, 1 mole of magnesium carbonate produces 1 mole of carbon dioxide. 0.1 moles of magnesium carbonate produces 0.1 moles of carbon dioxide. And then step 3, convert that numbers of moles into a gas volume by multiplying by the molar gas volume. I'm using decimeters cubed. So 0.1 times 24 comes to 2.4 decimeters cubed. So we can predict that 8.4 grams of magnesium carbonate produces 2.4 decimeters cubed of carbon dioxide. Here is a problem for you to complete. Given the balanced chemical equation for the reaction of hydrogen and oxygen to make water, calculate the mass of water formed by the complete reaction of 240 centimeters cubed of oxygen. So calculate the mass of water from an initial volume of oxygen. Pause, complete the calculation, come back to check and correct when you are ready. So I'm about to reveal. The first step is, of course, to convert 240 centimeters cubed into a numbers of moles, which I achieve by dividing by 24,000. Then I predict the moles of water produced. It's a 1:2 ratio between oxygen and water. So 1 mole of oxygen makes 2 moles of water. So my moles of oxygen is multiplied by 2 to give us the moles of water. So that's 0.02 moles. And I then convert that into a mass by multiplying by the mass of 1 mole. So the mass of water is the numbers of moles, 0.02 times the molar mass, 18, comes to 0.36 grams. GCSE, you may also meet reactions where both reactants and products, or all reactants and products, are in the gaseous state, in which case the mole ratio, or the reacting mole ratio of 2:1:2, as for this balanced equation, is also a volume ratio. 2 volumes react with 1 volume to make 2 volumes. This is a consequence of the molar gas volume. 1 mole of any gas occupies the same volume. So 2 moles to 1 mole is the same as 2 volumes to 1 volume to 2 volumes, etc. So let's have a look at the sort of problems and solutions that can result. Look at problem number 1. I'm going to model this. Starting with 4 decimeters cubed of carbon monoxide, what would be the volume of the carbon dioxide produced? So 2 volumes of carbon monoxide form 2 volumes of carbon dioxide. So 4 decimeters cubed of carbon monoxide would form 4 decimeters cubed of carbon dioxide. So could you complete question 2, starting with 5 of oxygen, what is the volume of carbon dioxide? And question 3, starting with 200 centimeters cubed of carbon monoxide, what would be the reacting volume of oxygen and the product volume of carbon dioxide? Pause, complete your calculation, come back to check and correct. Okay, so 5 decimeters cubed, it's a 1 volume to 2 volume ratio, so we would have 10 decimeters cubed formed of carbon dioxide. 5 forms 10. 1 volume forms 2 volumes. Question 3, well, 200 centimeters cubed would react with 100 centimeters cubed of oxygen to make 200 centimeters cubed of carbon dioxide. It's a 2:1:2 volume ratio. So for this type of topic, I think you need to practice. Start with your textbook or online. Use problems where you have access to answers. When you're consistently correct, then move on to past paper questions. If you've got some feedback about the lesson, I'll be grateful for a comment or a like. Or if you feel so inclined, please do subscribe.